Good morning. In this video, we are going to discuss an important topic of mathematics from class 12th. Solution of a system of linear equations using inverse of a matrix. We call this method matrix method also. In this method, we shall use some basic terms like singular and non-singular matrices, minors, cofactors, adjoint of a matrix, inverse of a matrix, etc. So for better understanding of this method, first we go through these concepts. It is advisable to get proper knowledge of these terms as they form the basis for this method. So let's discuss these terms one by one. Our first topic is singular and non-singular matrices. What is a singular matrix? Let's define it first. A square matrix A is said to be a singular matrix if its determinant is 0. Means if the determinant of a square matrix is 0, then it is called a singular matrix. We have given two examples, A 2, 3, 4, 6. Let's check whether it is singular or not. We find out its determinant. Its determinant will be, because it is a 2 by 2 matrix, so we can find out its determinant easily. It will be 2 into 6 minus 4 into 3, that is 12, minus 12, that is 0. So it is a singular matrix. Let's take another example of a 3 by 3 matrix this time. So determinant of this matrix will be 3 minus 1 2 2 1 3 1 minus 2 minus 1. Let's expand it along R1. So we get the determinant. You have practiced this method. What is the method? We are expanding it along R1. So A11. Now we hide the row and the column in which this element is positioned. So we convert this determinant into a 2 by 2 order determinant. So we get here 1 3 minus 2 minus 1. We get negative sign for this element, plus 1, and it is in first row and second column, so we get a determinant 2 3 1 minus 1, and this element is written with its original sign 2, and when it is reduced to a 2 by 2 order determinant, we get 2 1 1 minus 2. Now we evaluate this determinant. What we get? 3 into minus 1 plus 6 plus 1 into minus 2 minus 3 plus 2 into minus 4 minus 1. So we get 5 into 3, 15, plus 1 into minus 5 plus 2 into minus 5, that is 15 minus 5 minus 10, that is 15 minus 15, that is 0. So it is also a singular matrix because its determinant is 0. non-singular matrix. It is defined as a square matrix A is said to be a non-singular matrix if its determinant is non-zero. That is, if determinant of a matrix is not zero, then it is a non-singular matrix. That is, it is not singular means its determinant is not equal to 0. Two examples are given. Let's see whether they are non-singular matrices or not. First we find out determinant of matrix A. Its determinant will be, we calculate it directly, 2 into 3, that is 6, minus 4 into minus 2, that is plus 8. So its determinant is 14, that is not equal to 0. So it is a non-singular matrix. Similarly, we find out the determinant of matrix B. We evaluate it along R1. So 2 into minus 2 minus 4 plus 4. Opposite sign of this element plus 3. We delete the rows and columns of this element and we get the determinant 3 minus 4 1 minus 2. And when we multiply, minus 6 plus 4 plus 5, deleting the corresponding row and column, we get 3 minus 2. That is 2 into 0 plus 3 into minus 2 plus 5 into 1. So we get 0 minus 6 plus 5, that is value of determinant is minus 1, that is not equal to 0. So this matrix B is a non-singular matrix. Now you have to keep one thing in your mind, that inverse exists for a non-singular matrix only. That is, if determinant of a matrix is not equal to 0, then only we can find out its inverse. If the determinant of a matrix is 0, then we cannot find out its inverse. Next topic is minors. Minor of an element aij of a determinant is the determinant obtained by deleting its ith row and jth column in which element aij lies. Minor of an element aij is denoted by capital Mij. Let's take an example. Let A is a matrix of order 2 by 2 and we have to find out minors of its elements. It has got 4 elements, A11, A12, A21 and A22. So we shall have 4 minors in all. Minor of A11, as per definition, it will be capital M11. And how shall we get it? It will be obtained by deleting the concerned row and column of the position of this element. A11 lies here, it lies in first row and first column, so we delete first row and first column. Then what we get? We get element 3. So determinant of this element will be minor of A11, that is 3, because determinant of a single element is that element itself. Similarly, minor of A12, this element, it lies in first row and second column. So when we delete first row and second column, we get 4. So determinant of 4 will be minor of A12, that is 4. Similarly, minor of this element A21, it will be capital M21. It lies in, this element lies in second row and first column. So by deleting second row and first column, we get minus 2. So determinant of minus 2, that is minus 2. Similarly, minor of this element, its position is A22. It will be capital M22, and it will be obtained by deleting second row and second column, that is determinant of 2, that is 2. Now a 3 by 3 order matrix, we have to find out minors of this matrix. It has got 9 elements, so 9 minors will be there. We can follow the same method. So minor of this element, so minor of element A11, it will be written as capital M11, and it is obtained by deleting first row and first column, and then the value of the deleted determinant, reduced determinant, will be the minor of this element. So we get determinant 2 minus 4 1 minus 2, so its minor will be minus 4 plus 4, that is 0. Similarly, minor of element A12, it will be written as capital M12. The reduced determinant will be 3 minus 4 1 minus 2, and we get our minor as minus 6 plus 4, that is minus 2. Similarly, minor of element A13, that is this element, it will be capital M13. It will be obtained by deleting first row and third column, then the reduced determinant will be 3 2 1 1, and the value of minor will be 3 minus 2, that is 1. Similarly, we can find out the remaining minors. Cofactors. Cofactors of an element Aij of a determinant is denoted by capital Aij. It is defined as Aij equal to minus 1 raised to power I plus j into capital Mij, where Mij is the minor of element Aij. So from here we can see that the cofactor of an element of a determinant is related to its minor. We have to put a negative or positive sign before the minor to get its cofactor. See how? Suppose we have to find out the cofactor of this element A11. So it will be written as cofactor of element A11. It will be capital A11, and it will be minus 1 raised to power 1 plus 1 into M11, that is minus 1 raised to power 2 into M11. M11 is 0, so we get A11 equal to minus 1 raised to power 2, it will be positive, so overall we get 0. Similarly, cofactor of element A12, this element, it will be capital A12, that is minus 1 raised to power 1 plus 2 into M12, its minor, that is minus 1 into M12, and M12 is minus 2, so minus 1 into minus 2 we get plus 2. Similarly, cofactor of element A13, that is this element, it will be capital A13, and it will be minus 1 into M13, that is minus 1 raised to power 4 into M13, and M13 is 1, so we get plus 1. Similarly, cofactor of this element A21, it will be capital A21, and it will be minus 1 raised to power 2 plus 1 into M21, that is minus 1 raised to power 3, that is odd power, into M21, and M21 is 1, so we get minus 1. So what is the basic difference between a minor and a cofactor. We see from here that a cofactor of an element is very closely related to its minor. There is a difference of negative sign only, and when and where this difference occurs, it's due to position of an element. If the sum of suffixes of the element is an even power, then the minor of element is equal to its cofactor. If the sum of suffixes is an odd number, then we have to put a negative sign before its minor. So cofactor of A22 element, it will be capital A22. This element, it will be minus 1 raised to power 2 plus 2. It will give positive sign into M22, that is M22, that is equal to M22, and M22 is minus 9. So here minor will be cofactor for this element A22. Similarly, cofactor of element A23, it will be capital A23. It will be minus 1 raised to power 2 plus 3, sum is odd here, into M23, that is you have to put negative sign before the minor, and minor is 5, so you get minus 5. Similarly, cofactor of this element A31, it will be capital A31, that is minus 1 raised to power 3 plus 1, sum is even, into M31, and M31 is 2, so you get answer 2. Cofactor of element A32, that is this element, it will be capital A32, and it will be equal to minus 1 raised to power 3 plus 2 into M32, that is you have to put negative sign because sum is odd, and M32 is minus 23, so minus 23, it gives 23. Similarly, cofactor of element A33, this one, it will be capital A33, and it will be equal to minus 1 raised to power 3 plus 3, sum is even, into M33, and M33 is 13, so cofactor of this element is 13. So you have to keep one thing in your mind, that while calculating cofactors and minors, you have to be very careful, because even a single mistake can result in variation. Your answer may vary from the exact value. Adjoint of a matrix. Definition is, the adjoint of a square matrix A is equal to matrix Aij, is defined as the transpose of the matrix capital Aij, where capital Aij is the cofactor of the element Aij. Adjoint of a matrix A is denoted by ADJ capital A, that is adjoint of matrix A. So what is the method for finding adjoint of a matrix? For finding adjoint of a matrix, first of all you have to find out cofactors of elements of determinant, and then you have to put those cofactors at their respective positions. See, adjoint of this matrix will be the transpose of matrix of cofactors so obtained. That is A11, A12, A13, A21, A22, A23, A31, A32, A32. You have to put the values of these cofactors and then you have to take the transpose of this matrix. So adjoint, what is adjoint? Adjoint is the matrix obtained by taking transpose of matrix of their cofactors. We put the values of cofactors at their respective positions. So we get a matrix 0 to 1, minus 1, minus 9, minus 5, 2, 23 and 13. To get the adjoint of this matrix, we will have to take the transpose of this matrix. So adjoint will be, you have to change the rows into columns. First row into first column, second row into second column. So you get minus 1, minus 9, minus 5, third row into third column, 2, 23, 13. So what is the method to find adjoint of a matrix? First of all, we have to find out cofactors of each element. We have to write them at their respective positions and then take transpose of the matrix so obtained. Then we will get adjoint of that matrix. Inverse of a matrix. Inverse of a matrix is given by this formula. A inverse is equal to 1 by A determinant into adjoint of this matrix. That is, if we divide adjoint of the given matrix by its determinant, then we get inverse of that matrix. We have worked on this matrix. We know its determinant and its adjoint also. Its determinant is minus 1 and adjoint A is 0, minus 1, 2, 2, minus 9, 23, 1, minus 5, 13. So inverse of this matrix will be 1 by A determinant, that is minus 1, into adjoint of this matrix, that is 0, minus 1, 2, 2, minus 9, 23, 1, minus 5, 13. That is, you have to multiply this sign inside the matrix. So what we get? We get 0, 1, minus 2, minus 2, 9, minus 23, minus 1, plus 5, minus 13. This is inverse of this given matrix A. So from here you can see, if determinant of this matrix is 0, then we will get 0 in denominator and we will get an undefined term. We will never find its inverse. So you have to remember that if determinant of a matrix is 0, then inverse of that matrix does not exist. That is, for inverse of a matrix to exist, the matrix should be a non-singular matrix. Having discussed our basic concepts, let's move to our main topic: solution of system of linear equations using matrix method, that is inverse. Before that, we have to remember two things about this system. One is consistent system. A system of equations is said to be consistent if its solution exists one or more, that is unique or infinitely many solutions. That is, if even a single solution exists or more than one solution exists, then system of equations is consistent. An inconsistent system, a system of equations is said to be inconsistent if its solution does not exist. If any solution exists, be it one or more than one, then system of equations is called consistent system. If no solution exists, then system is called inconsistent. Let's consider the system of equations in three variables: a1x plus b1y plus c1z equal to d1, a2x plus b2y plus c2z equal to d2, and a3x plus b3y plus c3z equal to d3. Here x, y, z are variables. We have learned in the chapter of matrices that it can be broken into three matrices. Matrix A will be the matrix of coefficients of these variables. Matrix X will be column matrix of these variables, and matrix B will be a column matrix of these elements. We have seen it in chapter of matrices that if we multiply A and X, we get this form, that is AX equal to B. Now two cases arise from here. Case 1, if A is non-singular, that is determinant of matrix A is non-zero, then its inverse exists. Now we have AX equal to B. We are pre-multiplying both sides by A inverse. Pre-multiplying means we are multiplying, pre means before. It means we are multiplying both sides by A inverse by placing A inverse before these two matrices. There is another type of multiplication for this type, that is post multiplying. Post means after. If you post multiply these matrices, then you multiply as B into A inverse. AX A inverse equal to B A inverse. That is after. You are placing A inverse after these two matrices, after the matrices on both sides. The reason is very simple. We know that matrix multiplication is not commutative. We have to put A inverse together with A. If we multiply it like this, if we post multiply these two sides, then A inverse and A, they will be separated by X. They cannot neutralize each other. So we have to pre-multiply both sides so that A inverse and A both can cancel each other and we may get one, that is identity matrix. We can regroup these two matrices. We can group A inverse and A and separate X, because we are not changing their positions. Positions are same. We are simply bracketing in a new way. So what we get? A inverse into A equal to I, because when a matrix is multiplied by its inverse, we get 1, that is identity matrix. And when identity matrix is multiplied to a matrix, we get that matrix itself, that is X. So X equal to A inverse into B. So what is the procedure? We have to find out values of X, Y, Z. That is, we have to solve the system of linear equations. So we have to multiply inverse of matrix A by matrix B, and we shall find out the values of X, Y, Z. Now since the inverse of a matrix is unique, we get a unique solution for the given system of equations. That is, the set of values of X, Y and Z is single one only. Case 2. If determinant of this matrix is 0, in this case we calculate adjoint A into B. Again, two cases arise from here. If adjoint A into B is not equal to 0, then no solution exists for this system of equations and it is inconsistent. Second case, if adjoint A into B is 0, then system may be either consistent or inconsistent. Accordingly, the system may have either infinitely many solutions or no solutions. So we can summarize both cases in this chart. Let's take an example. Solve the system of linear equations using matrix method. 2x minus 3y plus 5z equal to 11, 3x plus 2y minus 4z equal to minus 5, x plus y minus 2z equal to minus 3. Here we can write it into three matrices A, X and B. Now we know that Ax equal to B. So from here X will be A inverse into B. We have learnt it in the concept of inverse. So we put the values of three matrices X, A and B. What do we get? X, that is X, Y, Z is equal to A inverse. We know the inverse of this matrix. It is 0, 1, minus 2, minus 2, 9, minus 23, minus 1, 5, minus 13 into B, and B matrix is 11, minus 5, minus 3. Now order of this matrix is 3 by 3 and order of this matrix is 3 by 1. So by property of matrix multiplication, both matrices can be multiplied, and we multiply the rows of this matrix by column of this matrix, and we know that the product of this matrix with this matrix will give us a matrix of order 3 by 1. So multiply these two matrices and we get 0 into 11, 0, 1 into minus 5, minus 5, minus 2 into minus 3, plus 6. Second row with first column, that is we get a to 1 element of answer matrix. Minus 2 into 11, minus 22, 9 into minus 5, minus 45, minus 23 into minus 3, plus 69. Minus 1 into 11, minus 11, 5 into minus 5, minus 25, minus 13 into minus 3, plus 39. It is equal to this matrix. So we simplify these two matrices and we get 1, 2 and 3. So equating the corresponding terms, we get our answer: x equal to 1, y equal to 2, and z equal to 3. This is our solution, and this solution is unique. We can't get another set of values for x, y and z. I hope this method will be clear to you now. If you have any doubt, please rewind the video. Let's take another example. For the matrix A, show that a cube minus 6a square plus 9a minus 4i is equal to 0 matrix, and hence find A inverse. There are two parts in this question. In first part, you have to show that it gives a 0 matrix, and using this result you have to find inverse of this given matrix. So this is another method of finding inverse of a given matrix. By now you have learned to find inverse of a matrix by elementary transformations by using adjoints, and this is a different method. In this method we shall make use of properties of matrix multiplication, addition and subtractions only. So first of all we prove the first part. So first we find out a square, and a square will be given by a into a, that is, so multiplying a by itself we get a square by matrix multiplication. You are now well versed in this method and it is expected from you also. Now we find out a cube, and a cube will be obtained by multiplying a square by a. So a cube will be given by a square into a. So we get a cube equal to this matrix. Now write down the left hand side of first part. It is a cube minus 6a square plus 9a minus 4i. Now put the values of a cube, a square, a and identity to solve it. Putting the values of a cube, a square, a and identity, we get this expression. Now we have to simplify this expression. So on solving this matrix we get 0 0 0 0 0 0 0 0 0. So first part is verified. This is equal to 0 matrix. Now see the second part. Using this result, now we have to find out inverse of this matrix. Originally we were given this equation. Now we pre-multiply both sides by A inverse. Pre-multiplying both sides by A inverse, that is A inverse into A3 minus 6 into A inverse into A square plus 9 A inverse into A minus 4 A inverse into I equal to A inverse into 0 matrix. Here 6, 9 and 4, these are constants, so A inverse can be written after them. So we get A square minus 6A plus 9 A inverse into A gives identity matrix minus 4 A inverse into I, it gives 4A inverse. Now take 4 A inverse to right hand side. So we get A square minus 6A plus 9I is equal to 4A inverse, or 4A inverse is equal to A square minus 6A plus 9I, that is A inverse will be 1 by 4 into A square minus 6A plus 9i. That is, we have to simplify a square minus 6a plus 9i and divide that result by 4, and we will get inverse of this matrix A. So placing the values of a square, a and I in this equation, we get a inverse equal to this one. Now we simplify these and we get, so on simplifying we get a inverse equal to 1 by 4 into 3 1 minus 1 1 3 1 minus 1 1 3. You can verify your answer by using adjoint method. Answer will be same. I hope this